So we discussed an example where we created space partition constraints, and then we basically saw what it would look like in a 2D diagram. We took an example which had a loop nest of depth 2, and then we just gave the solution and said, look, here's a solution, and you can verify for yourself that this solution satisfies the constraints. We're going to look at it in a more mathematical sense today, instead of looking at it just from a pictorial representation and convincing ourselves that the solution works. Let's look at it from a mathematical standpoint to convince ourselves that the solution actually works, even from a mathematical standpoint. So it's the same loop that we had earlier. For I equals 1 to 100, for j equals 1 to 100, xij equals xij plus yi minus 1j, and yij equals yij plus xij minus 1. And we said that the only data dependencies of consequence here are xij with xij minus 1 and yi minus 1j with yij, right? So these two and these two, the diagonal ones. Because the other ones are not going to make much difference, except for the fact that this entire statement has to have this entire C statement, which involves 3 memory accesses, should all be mapped to the same processor, and similarly for the second statement as well. So if you take that, then the only two kind of conflicting potentially accesses that could potentially have data dependencies are xij and xij minus 1 and yi minus 1j and yij. Okay. So when I look at xij and xij minus 1, so just taking one of these data dependency, pair of statements that have a data dependency, which is xij and xij minus 1, what do I need to do? What are the unknowns? The unknowns are C1, which is, C1 is the mapping function from S1 for S1, and so the coefficient matrix for S1, and small c1 is the additive vector for S1. Similarly, capital C2 is the coefficient matrix for S2, and small c2 is the additive vector for S2. So in other words, if my loop iteration indices for S1 were I1, J1, then the processor ID for the I1, J1 iteration count would be given by C1 into I1, J1 plus small c1. And similarly, for S2, we will use capital C2 and small c2. Okay, so what is the maximum rank that C1, capital C1 can have? Well, notice that the loop iteration nest itself is of depth 2. So the maximum loop nest, the dimension of the iteration space is 2. And so the maximum dimension of the processor space on which this is going to get mapped is also 2. And so from that, we basically get a square coefficient matrix. The number of columns represents the depth of the loop iteration nest, and the number of rows represents the size or the dimension of the processor matrix, the maximum dimension. And this is true for both capital C1 and capital C2, and also small c1 and small c2, because the additive constants will have 2 rows each. Now, when I look at this, one thing that I would going to, now basically I want to solve for capital C1, and so when I solve for capital C1, basically means I need to figure out what are the values for each of the elements in this matrix. There are 4 elements in this matrix, and so I have named them so that I can easily refer to them. That's C111, C112, C121, C122. Similarly, C211, C212, C221, and C222. So there are 8 such unknowns in the coefficient matrix, and similarly small c11 and small c12, small c21 and small c22 are the unknowns in the additive vectors. And I want to solve for these unknowns. Now, one thing that I'm going to tell you upfront about this problem from what we know from the previous module is that I know that the best solution for this is going to be a one-dimensional processor space mapping, which means the dimension of the processor space on which this is going to get mapped, this loop iteration space is going to map, is going to have one dimension of 1. So that's the value of k that we have been using in our previous discussion, where k is the dimension of the processor space. How do I know that? Well, that's from, that's just, I'm using the previous knowledge that we have from the figure, where basically there are n number of two n number of independent chains, and 2n is basically a linear number in the in one dimension, which is order n. So, or in other two, n is 100 in this case. So that's basically the number of independent parallel processing threads that you can create maximum is basically linear in the size of one dimension. On the other hand, if there were no data dependencies, then the processor space would have been two-dimensional. And so what does this mean? What do I know just from this previous knowledge? In general, when we are solving for this, we won't have this previous knowledge, but just to make the discussion simpler and easy to kind of communicate, I'm using the previous knowledge. And so what does it mean based on the fact that we already know that the processor space that we're going to map the iteration space to is going to be one-dimensional? It basically means that this matrix, capital C1, is going to have a rank of 1. Okay? In other words, there's going to be only one linearly independent row in this matrix. The second row will be dependent. In other words, I can specify, I can C121 and C122 can be always specified as linear multiples of C111 and C112. In other words, when I can always kind of bring this matrix to an echelon form, and so basically what I can say is that because it is rank 1, I can always bring it to a form where the last row, the second row, is always 0. Okay, so this is 0 and this is 0. And if the row, because it's going to be a rank, I already kind of from my previous discussion know that's going to be 0. Now, when I'm going to actually solve the equation in on a computer or something like that, I won't have this information. In which case, I am going to have all the 4 unknowns here, and then I'm going to solve for them. And then from that solution itself, it will become apparent that these matrices are rank 1. But I don't want to go through the entire solution in my discussion today, so I'm just making it simpler by just noticing that I'm sure that the last row is going to come out to be a linearly dependent row on the first row because I know that the solution is going to be rank 1 matrix, and so I'm just going to simplify the discussion by just assuming that I can just strike out this second row. In other words, I can just make this row 0. And similarly, I can strike out the row from the additive vector as well, which is the small c's. Okay, and so with this discussion, this is our new problem. Capital C1 has 2 unknowns, and now I can use a smaller number of unknowns. Also, the naming becomes easier, so it's just C11 and C12 instead of C111 and C112 and stuff like that. And now C2 is C21 and C22. Once again, I've made this simplification just for discussion purposes. In an actual implementation, you would basically optimistically assume that the matrix may be full rank, and then when you get to the solution, you're going to find, oh, the rank of the matrix is actually 1, and then it is at that point that you're going to remove the last row. So I'm just removing the last row up front so that the discussion becomes easier. All right, so now I have to solve for all these unknowns. So how many unknowns are there? There are 1, 2, 3, 4, 5, 6. All right, so there are 6 unknowns here, and that I need to solve for. And what are the constraints? It's the same space partitioning constraints that we have already seen. So what are the space partitioning constraints? The space partitioning constraints are that when I use C1, when I multiply this with the iteration vector plus C1 should be equal for different values of I1 J1 and I1 prime J1 prime. They should be mapping to the same location in the processor space, or the same PID in the processor space, if there was a data dependency between I1 J1 and I1 prime J1 prime. And similarly for I2, for the statement S2, in which case it will be I2 J2 and I2 prime J2 prime. And similarly across S1 and S2. All right. So for example, because both the iteration space of both S1 and S2 are equal, across these things also going to be I1 J1 and I2 prime J2 prime. Okay, so here are my space partitioning constraints as we know them. If I is less than equal to 100, so I'm not using I1 and J1 now because, as I said, both S1 and S2 have the same iteration space. So let's just use I and J because it's going to be the same iteration space. So if I is less than equal to 100 and J is less than equal to 100 for S1, and then if I prime is less than equal to 100, and greater than equal to 1, and J prime is less than equal to 100 and greater than equal to 1, and there is a data dependency between xij and xij minus 1. So what does that mean? It basically means that xij is pointing to the same location as xi prime comma j prime minus 1. In other words, when will these two locations point to the same thing? When I is equal to I prime and j equals j prime minus 1. So that's our constraint. That's coming from our fi plus small f equals f prime I prime plus small f prime. So capital F and small f are coming from I comma j. Capital F prime and small f prime are coming from I comma j minus 1. Alright, so basically what I get is I equals I prime and j equals j prime minus 1. So my constraint is that if all these conditions are true for all such values of I and I prime and j prime, whenever this condition is true, it must be true that C11, C12 multiplied with ij plus small c1 equals C21, C22 multiplied by I prime j prime plus small c2. So whenever this is true for all possible values of I, j, I prime, j prime. Okay, so I need to solve this equation, and I'm going to propose some. So once again, I'm not going to discuss the algorithm to solve the solution, but I'm going to propose some potential solutions and basically get a sense of what this problem, what is the nature of this problem. So here is here is one possible solution. So I want to find a solution to C11 and C12 and similarly small c1 and capital C21 and C22 and small c2 such that these constraints are satisfied. Now notice that whenever I equals I prime and j equals j prime minus 1, these should be equal. So here is one simple idea, that what if I just say that C12 equals 0 and C11 equals 1. Alright, and similarly C21 equals 1 and C22 equals 0. In other words, the coefficient of I is 1 and the coefficient of j is 0. In which case, basically because whenever I is equal to I prime, this is going to be, the processor that this is going to map to is I, and let's say small c1 and small c2 are also 0. So then this processor, the processor indicated by, the PID indicated by the LHS of this equation is going to be just I. Alright, so here is my proposed solution. Small c1 equals c2 equals 0, capital C11 equals capital C21 equals 1, similarly capital C12 equals capital C22 equals 0. I claim that with this solution all these constraints are getting satisfied. Okay, so why? Let's see. If capital C11 equals 1 and capital C12 equals 0, that's what these constraints say, then this becomes just I, and small c1 equals 0. So this whole thing becomes I. Similarly, this whole thing becomes I prime, right? Because capital C21 is 1, capital C22 is 0, small c2 is 0. So whenever I is equal to I prime, this becomes I and this becomes I prime, and I know I equals I prime, so the process ID was also I and I prime, which are equal, and so these constraints are getting satisfied. Now I'm not claiming that this is the maximum rank solution. Actually, it turns out that the maximum rank solution, if the only constraint was this constraint, then the maximum rank solution would have been a rank 2 solution, and I'm just working with a rank 1 solution. But this is one of the possible solutions which may not be the maximum rank solution. It is not as dumb as a trivial solution. Of course, the trivial solution is both C11 and C12 are 0, and similarly C21 and C22 are 0. So everything is 0, which is the trivial rank 0 solution, and I'm not interested in that. But I have a better solution, which is C11 is 1 and C12 is 0, and C21 is 1 and C22 is 0, and these additive coefficients are also 0. In which case, these constraints are going to get satisfied. Okay, but this is not the only constraint I have in the program. So let's remember the solution. The solution is that the coefficients of I are 1 and coefficients of j are 0. J and j prime are 0 and I prime are 1. Now let's look at the other constraint, which is coming from Yij and Yi minus 1j. So this is the other constraint that's coming from Yi minus 1j and Yij. And once again, I set up my equations. The only difference is that now the capital F and small f and capital F prime and small f prime are different. Capital F and small f are relating to Yij, and capital F prime and small f prime are relating to Yi minus 1j. And so now my space partitioning constraints are whenever I minus 1, which is coming from S1, equals I prime, which is coming from S2, and J, which is coming from S1, and J prime, which is coming from S2. Then then the same thing, right? C11 C into Ij plus small c equals C2 into I prime J prime plus small c2. Now, just like I had done in my previous slide, I can make the same observation that here it's J equals J prime. So what I can do is, one solution to this this whole thing could be that let's just put a coefficient of J to be 1 and coefficient of I to be 0, and that would be a solution to this set of equation, this particular equation. But now this is not going to be a valid solution for the previous constraints that I had on the previous slide. So I want a solution I want a solution that satisfies both the constraints, and that makes the problem interesting, isn't it? So the first thing I want to point out is that the solution that I had in the previous slide is not going to satisfy the constraints on this slide. So recall that the previous slide, the solution was coefficients of I, which are C11 and C21 are 1, and coefficients of J are C1, which are C12 and C22 are 0. And if I do that, then I get, and then the additive constants are 0. Then if I do that, then I get I plus 0, which is I, and here I get I prime. And it's not, but I is not equal to I prime. I prime equals I minus 1 in the preconditions. So this is not going to work, right? So this solution is not going to satisfy this constraint, because whenever I minus 1 equals I prime, it is not true that I equals I prime. And so this solution does not satisfy the constraint on this slide. So recall that this is the solution that we had for the previous set of constraints on the previous slide. Now here is another possible solution, and the solution is that I put the coefficients of J and J prime to be 1 and coefficients of I and I prime to be 0. So just flip, and now it satisfies the solution, the constraints on this slide, because now whenever J equals J prime, the processor IDs that the two statements map to are going to be same. But then this does not satisfy the constraints on the previous slide for the same reason. And I claim that here is a solution which satisfies both the constraints, and the solution is that you have all the coefficients of I to be 1, so C11, C21 is 1, coefficients of J to be minus 1, so C12 and C22 are minus 1, and the additive constants are also important. C1 is minus 1 and C2 equals 0. So let's see. Whenever I minus 1 equals I prime and J equals J prime, then C11 becomes 1, so this becomes 1. C12 becomes minus 1. Similarly, C21 becomes 1 and C22 becomes minus 1. C1 becomes minus 1 and this becomes 0. And so this becomes I minus J minus 1 equals I prime minus J prime plus 0. So I'm just not writing the 0. And is it true that whenever I minus 1 equals I prime and J equals J prime, I minus J minus 1 equals I prime minus J prime? Well, because J equals J prime, I can just eliminate J and J prime on both sides, and then I'm remaining with I minus 1 equals I prime, and that's true because of this constraint. So indeed, this solution that I have, which is C1 equals minus capital C11 capital C21 equals 1, capital C12 capital C22 equals minus 1, and small c1 equals minus 1, small c2 equals 0, satisfies the constraints on this slide. And I claim that you can try this solution also on the constraints that I had on the previous slide, and you would find that this set of this solution satisfies those constraints as well. So now we have a solution that satisfies both sets of constraints, unlike the previous two solutions which satisfied only one of the constraints.